Hello and welcome back to my favorite people. I'm here with another lecture from organic chemistry. In this lecture, we will start a new chapter, and it's going to be conjugated pi system and pericyclic reaction. We'll start discussion by talking about dienes. Dienes are compounds that they have two double bonds, and that's the reason we say diene. Di stand for two, and ene stand for a double bond. Now, the double bonds, they can be back-to-back without any space between them. In that case, we say accumulated, or there is one single bond maybe between them. If there is a single bond between the two pi bonds, then we call it conjugated. And if we have more than one single bond, and in that case, we call it, we call the compound, or we classify it as isolated diene. Okay, now what's the difference between accumulated, conjugated, and isolated? The accumulated, as you see, for the first pi bond, let's say we decided to use two p orbital. I go with, for example, pz. They are aligned, and I can line with the z-axis, and say this one is positive, positive. And now for the second pi bond, I can put another pz orbital here and expect it to make it the second pi bond for me. The reason for it, because I used this pi bond to make a double bond here. So that one, the one in the middle, is already used. And now, and the way we get a second pi bond is to use another p orbital, and this is going to be either px or py. And so as you see, the first double bond, it will be perpendicular to the second and double bond, and they will be in different planes. And because they are not talking to each other, or they have 90 degrees between them, and we don't expect the electron to jump, for example, from this plane to a perpendicular one. And so this system is not going to be that stable technically. Okay, next one, it will be the conjugated. The conjugated, as you see, we have a space, technically space between the two double bonds, one single bond, and but that's going to give us a chance to put, to use p orbitals from same type. So I'm going to use pz. All of them are pz. They will be aligned with each other, and we can actually transfer the electron from one orbital to another orbital. And so we say we have a conjugated system, or technically we can have resonance. And how about the isolated? The isolated, you will have a spacer between the double bonds, and that spacer is going to have sp3 hybridization, and because it's already saturated, we cannot run any resonance structure, and because we don't have a resonance structure, so it's not going to be as stable as conjugated system. How do we get dienes? One way to get dienes is to technically run elimination reaction. So this one is an elimination reaction by using bulky group. And remember, if you're using a bulky base, that base is going to favor Hoffman product instead of Zaitsev product. What do I mean by Hoffman product? And in the Zaitsev product, we said the double bond, it will be built wherever, like it will be built in a way that you get more substituent, and so it will be more stable. While if you decide to put here, like because of steric effect, if you decide to make a terminal, technically terminal alkene, or an alkene with less substituents, we call it Hoffman product. Thermodynamically is less stable than Zaitsev product. So this one is more stable, and the second one is less stable. Okay, now that we know if we use bulky base, we can get like a double bond. So how about this? So we can start with such a compound, and that it has halide, and that base is going to remove H. Well, as H is taken by the base that it has a lone pair, it will go after that H, and that H, it will share an electron here with carbon, and that bromide, it will take the lone pair, or those two electrons, will take those two electrons, and it will leave the system, and it will give us double bond. Now, if you have a two halide or halide compound, then you can start from alkyne instead of alkene and get the diene products. Now, let's talk about the bond length in a conjugated system. And so we said this one, we're going to call it a conjugated system, and there is a spacer here. There is a single bond between the two double bonds. That single bond, when we compare it with ethane, is shorter. And what's the reasoning behind it? The reasoning behind it, we said those carbons, they have sp2 hybridization versus sp3 hybridization. sp2 orbitals are smaller than sp3 orbital. What's the reason behind it? Because they have more s character. In this case, we have 33% s character, and 70 or equals 67 or 66.66% is going to be a p character. Well, here is just a 25% s character and 75% p character. The more s character in the orbital has, the closer it will be to the nucleus, and that means the bond, it will be shorter because the orbital is going to be smaller, and because it's smaller, it will give you shorter orbital. That's one way to look at it. And another way to look at it, you can take this pi bond and move it here and see what will happen. And of course, if you move it there, then this one is going to move to the terminal carbon. If we draw such a resonance, we will get this structure. we will have a positive charge here, we get a negative charge there, and there will be a double bond there. So the bond that we're talking about, the one I'm going to highlight, that bond, sometime it will be double bond instead of single bond. And because it has double bond character, it will be shorter than a regular single bond. And so that's one way to technically justify why this bond is shorter than a plain single bond. And later, I'm going to use the molecular orbital to justify why this bond is, again, shorter than a single bond. Now let's talk about the delta H of hydrogenation, or like how much heat technically we get whenever we give a double bond and we give it hydrogen atoms, or technically we saturated it. So I'm gonna start with like diene. Okay, diene, and I will give it 2 mole of hydrogen. Why 2 mole? Because I have 2 pi system, 2 pi bonds, 1 pi here, another pi here. Per each pi, I need to add 1 mole of hydrogen. Before I continue discussion about this, I need to remind you about the delta H. First of all, delta H is the gap between reactant and a product. Say we have such a system. So I'm going to say the gap between reactant and a product, I will call it the delta H. So this one is going to be delta H of the reaction, which is equal to Q of the reaction. Now, this one is a product, that's reactant. If energy, okay, energy of the product, let's say delta H of the product is less than delta H of the reactant, in that case, we say delta H of the reaction, which is equal to number of mole for delta H of the product minus number of mole multiplied delta H of the reactant. This number, it will be negative. That means it will be exothermic, will release heat. So the sign for Q, it will be negative, and also for delta H is going to be negative. And next one is like, let's say we have A is turning to C, and we have also, let's say we have B is turning to C. I got delta H of this reaction is equal to minus 200 kilojoule per mole. And delta H of the second reaction, let's say we got this one minus 250 kilojoule per mole. Now, I want to talk about which one of this is more stable, okay? A or B. And how do we judge it? We judge it based on like how much heat they release, when they turn to C. And in this case, the second one, B, is going to be less stable. B is less stable than A. Why? Because when we turn it to C, we got more energy. Okay, we got more energy. So I'm going to say this one gave me heat. That one also gave me heat. So where do I put A and like an A and B? The way I'm going to position those two. Okay, again, I will draw a graph and say this one is C. Let's say that one is going to be A, and B, I'm going to put it somewhere here. Okay, they might go different pathways to give us the final product. Okay, so I go this one. If this one is a transition state, sorry, like the graph for A to C, that's going to be the gap for sorry, like the pathway for B to C. And again, we said the delta H is going to be the gap between reactant and product. That's delta is going to be delta H of A to C. Delta H for A to C. All that this one is going to be delta H. That's going to be delta H for B to C. So as you see, delta H here, delta H for B to C is bigger than delta H of A to C. That means it's telling me B is sitting in higher level of energy than A. So B is less stable. Right. B is less stable. Now that we have this knowledge, let's go back and compare the diene versus an alkene. Okay, now I have two bonds and I saturated them by 2 mole of hydrogen. I got minus 200, I got 239 kilojoule heat. So we got this amount of heat or energy. Now we turn it to butane. I will start with an alkene of butane, and it has one double bond. And in order to compare it with the diene, we're going to use 2 mole from it. And so I will saturate this one, and clearly that's going to give me 2 moles. 2 mole from the butane plus again heat. Now, when I compare the heat, as you see, my minus 254 versus 239 is that's telling me that alkene is less stable than diene. Okay, alkene is less stable, so I'm gonna say diene is more stable. I mean, something is making it more stable. And now let's talk about that one. That is because we said we have a conjugated system, and all the pi bonds. If we go back here, all the pi bonds are or the p orbital, technically they are in one plane, and they are parallel, and they can actually we can build resonance structure between them. Okay, and that's the reason the system is going to be more stable.